Right, I just want to have a look at these questions because we didn't get around to doing them in class. So a 2 kilowatt. So before I do anything, I'm going to convert that into 2000 watts, and that's power. 230 volts. So 230 is my voltage. The current flowing in the heater. Oh, it's very thick. Ooh. So P equals VI, 2000 equals 230 times I, and then divide across by 230. So 2000 divided by 230 is 8.7. Shouldn't be there. So that's 8.7 amps for the current. The resistance, Ohm's law, V equals I or. Sorry, I'm just going back in here to have a look. Or is it P is I squared or? Could I use either, I wonder? Could I use either? Let's try. So V equals I or would be 230 is 8.7 times or, and divide across by 8.7, divide across by 8.7. So or is, I left the entire number in, so I'm getting 26.45 ohms. And then what if I did it? What was the power? 2000. So 2000 is 8.7 squared times or. So if we divide across by 8.7 squared, hang on. So that's squared, and then 2000 divided by that. Oh yeah, 26.45. So either formula will work there. And the time taken to produce 100 megajoules of heat. I mean, power is I squared or, and we can turn power into work over time, which is I squared or. And we can multiply across by T. 100 megajoules. So that is 100 by 10 to the 6 joules. So this is 100 by 10 to the 6. The current is 8.7. The resistance is 26.45. Times T. So that is 100 by 10 to the 6 equals 2000 by T. Divide across by 2000. So 50,000 seconds. Divided by 60, 833 minutes, 13.8 hours. I don't have my book here to check those answers. See if I can get it online. Anyway, I'll go on to the second one. So the second question is, sorry, that's question 9. Second question is question 13. Okay, so 2 kilograms. So mass is 2 kilograms of water at 10 degrees Celsius are placed in an electric kettle which operates on a 230 volt. Okay, so the voltage is 230 and we have an initial temperature of 10 degrees Celsius. If the current that flows in the kettle, which when it is switched on, is 9 amps, how long does it take to bring the water to the boil? Okay, so the final temperature, if we want to bring it to the boil, is 100 degrees Celsius. So the energy required, QE, whatever. The energy required to do that is MC delta theta. So it's going to be 2 by its water, so 4180. Yeah, 4180. And then the change in temperature is going to be 90. That's 752,400 joules. Can I get power from here? So P equals VI, which is 230 by 9. So that is 2070 watts or 2070 joules per second. Okay, so if it's 752,400 joules that we need, and this kettle will do 2070 every second, if I just divide them, I get 363.5 seconds it will take to bring the water to the boil. And then how much longer will it take for 3/4 of the water to boil off? So the energy, boil off is changing state. So that's going to be ml. M is going to be 1.5 is 3/4 of 2 kilograms. And the specific latent heat of vaporization is 2.3 by 10 to the 6. So that multiplied by 2.3 by 10 to the 6 is 3, 4, 5, 1, 2, 3, 4. So it's that many joules to boil off. So if it's 3, 4, 5, 1, 2, 3, 4 at 2070 joules per second, that is 1666.6 recurring seconds. So how much longer? Yeah. So that is 27.7 minutes to boil off 3/4. And that is 6.1 minutes to bring that much water to the boil. I'll check the answers and I'll make adjustments if I've made any errors, but hopefully I haven't. So yeah, there you go.